In episode 35, Sanitize Inputs and Handle Errors Without Leaks, we focus on two everyday disciplines that quietly carry huge security weight: stopping bad data at the boundary and keeping failures both calm and discreet. Many serious incidents begin with a single unchecked field or a verbose error that reveals just a bit too much about the system beneath. When you treat input handling and error behavior as first-class design choices, you reduce attack surface while also making your software easier to support. The goal is not to make systems silent and opaque, but to keep attackers starved of clues while operators receive what they need. Done well, this becomes a habit that runs through every endpoint and feature you touch. The first line of defense is to validate inputs at boundaries using clear schemas and explicit checks for length, range, and format. Boundaries include user interfaces, APIs, message queues, files, and any external data source entering your system. Schemas provide a contract for what valid looks like, defining required fields, allowed values, and nested structures in a way tools can enforce. Length and range checks prevent obvious abuse such as oversized payloads or impossible numeric values, while format checks like proper email patterns or date structures catch malformed content early. When validation is consistent at boundaries, many malicious or accidental problems are rejected before they have a chance to interact with deeper logic. Normalization and canonicalization are equally important because attackers often exploit differences in how systems interpret encodings. Normalizing encodings means turning inputs into a consistent form before validation and processing so that variations in case, escape sequences, or multi-byte representations do not bypass checks. Canonicalizing paths, URLs, and Unicode representations ensures that a seemingly harmless string does not resolve to a sensitive directory or unexpected location after internal processing. For example, handling ... segments and encoded slashes carefully prevents path traversal tricks that slip past naive filters. Treating normalization as part of the input pipeline helps you reason about data in a single, trusted shape, rather than chasing every possible disguise. Allow lists provide stronger guarantees than deny lists in many cases, because they define what is allowed rather than trying to enumerate everything that is forbidden. When you use strict allow lists, you say only these characters, ranges, or patterns are acceptable, which naturally excludes inventive payloads that an attacker might craft. Denial lists tend to lag behind attacker creativity, blocking known bad strings while failing to anticipate new combinations or encodings. In some contexts, like freeform text, allow lists may need to be more permissive, but even there you can constrain structure and length. The underlying principle is to restrict input to the smallest useful space, narrowing the room for harmful variation. When dangerous payloads are detected, your system should reject them decisively while still capturing enough context for later analysis. Rejection means halting further processing and avoiding partial execution that could leave state inconsistent or side effects half applied. Logging context does not require storing the full raw attack. You can capture metadata such as source, endpoint, timestamp, and a safely truncated or sanitized version of the input. This approach preserves evidence without keeping harmful content that might itself be exploitable or sensitive. By striking this balance, you give investigators what they need without turning logs into another liability. Parameter binding extends these protections into the commands your code issues to databases, operating systems, and external services. Instead of concatenating untrusted data into SQL statements, shell commands, or template strings, you bind values as parameters so that control and data remain separate. This technique dramatically reduces injection risk because the interpreter receives the structure of the command from trusted code and the variable parts from validated inputs. Binding should be treated as a default, not a special case security feature, across all data access layers and integrations. When you never build commands with raw concatenation, it becomes much harder for untrusted input to alter intent. On validation failures, robust systems fail closed and respond with minimal, generic client messages. Failing closed means refusing the operation rather than proceeding with relaxed assumptions or default behaviors that might be unsafe. Client-facing messages should avoid revealing which specific check failed, what the internal structure looks like, or what values might be expected. Instead, they can indicate that the request was invalid and suggest that the user verify their input. Detailed feedback for troubleshooting belongs on the server side, where it can be interpreted without helping attackers refine their strategies. This separation keeps the external surface simple while preserving depth for diagnosis. A key discipline is clearly distinguishing user messages from diagnostic logs so that each audience receives the right information. User messages must be short, understandable, and free of technical implementation details, focusing on what the person can reasonably do next. Diagnostic logs, by contrast, should record structured data about the error condition, including context, stack location, and relevant identifiers that help engineers track down issues. Keeping these two channels separate prevents support text from drifting into user-facing responses and stops sensitive technical context from leaking through to clients. Over time, this separation makes both support and security reviews much more manageable. Because errors and logs so often intersect with sensitive data, you need mechanisms to scrub secrets from logs, traces, and exceptions automatically at capture time. This involves defining which fields or patterns represent credentials, keys, tokens, or personal information, and ensuring they are masked or removed before any storage or forwarding occurs. Framework-level filters can intercept log events and trace spans, replacing sensitive values with placeholders, while still recording the presence of those fields. Doing this consistently reduces the risk that debugging information will become a repository of sensitive material waiting to be discovered. Secret scrubbing should be treated as a standing design requirement, not an afterthought. Stack traces and low-level exception details are invaluable for developers, but should never be displayed directly to users. When a failure occurs, users should receive a short, neutral message and a correlation identifier that they can provide to support teams. The correlation identifier allows you to look up the full diagnostic record internally, including stack trace, input context, and environmental details without exposing those details externally. This pattern preserves the ability to debug complex issues while keeping the user interface clean and secure. It also trains teams to rely on proper observability tooling instead of quick and dirty error displays. Handling errors safely also means implementing retry-safe operations that avoid amplifying traffic or creating inconsistent states. When clients or intermediaries automatically retry requests after timeouts or failures, your server-side logic must be idempotent or keyed with mechanisms like unique request identifiers. Without these patterns, a transient network issue can trigger repeated inserts, duplicated actions, or unintentional escalation of load. Designing for safe retries reduces the risk that error handling will create new vulnerabilities, such as resource exhaustion or replay opportunities. It turns recovery from failure into a controlled process rather than a chaotic storm of repeated attempts. Testing negative paths rigorously is the practical way to confirm that your input handling and error behaviors work as intended. This means simulating malformed inputs, oversized payloads, mismatched encodings, and adversarial patterns that attempt to bypass validation or trigger unusual states. Automated tests should assert not only that the system blocks harmful requests, but also that it returns appropriate, minimal messages and generates useful diagnostic logs. Regularly running such tests guards against regressions where new features accidentally loosen constraints or reintroduce verbose error output. By treating negative paths as first-class test targets, you keep these safeguards healthy over time. If you step back and summarize, effective input sanitation and error handling follow a consistent pattern. You validate and normalize data at boundaries, favor allow lists, and reject dangerous payloads decisively while using parameter binding for commands. You fail closed with minimal client messages, separate user feedback from diagnostic logs, scrub secrets from telemetry, and hide stack traces behind correlation identifiers. You design operations to tolerate retries without unintended effects, and test negative paths with adversarial inputs. These habits reinforce one another, turning everyday coding decisions into robust protection against common attack techniques. To close this episode with something concrete, choose one endpoint or input path in a system you work with and deliberately harden it. Add or tighten a validation schema, normalize its inputs, and verify that it fails closed with clean, generic client responses and useful internal logs. Check that no secrets slip into those logs and that stack traces never reach the user, relying instead on correlation identifiers you can trace. As you do this, add the key validation rule or pattern you used to your personal or team checklist. Each small, focused improvement like this makes future work safer by default. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.